If you could scan pores in someone's face, like that's even better than a fingerprint.
All right, so let's implement stacks. So one way to do this is using an array, and this is pretty typical. So again, I'm just going to work with stacks of integers, but this could be anything, okay, as long as your array manages whatever that type of data is. So let's do an array-based stack of integers. So I'm only going to make a stack that can hold 10 things. You'd probably make this bigger, but this is even smaller than a PIC processor. So integer stack 10. And I'm going to have an integer called a stack pointer. And the stack pointer tells you where the top of the stack is, which is important both when you're pushing and when you're popping. You got to know where the top is, where to put the plates, where to take the plates from. All right. And there's a variety of ways to do this. So let me give you one. SP is location for next push. And an empty stack is going to be stack pointer equals 0. Okay, these two decisions tell me how the stack is going to operate. So let's make our array. So here's stack. So it's got 10 locations, and here's my stack pointer. It's initialized to 0. Okay, SP tells me where the next value should get pushed. So the first time I push something onto the stack, it's going to go right here in element 0. So if I say push 15, that's going to go right here. And after doing that push, the top of my stack will move, so I'm going to increment my stack pointer to a 1. So now if I say push 20, SP tells me where I should push that number in my array. So since SP is 1, I'm going to store that 20 at index 1. And I'm going to increment my stack pointer. And if I say push 100, I look at my stack pointer, it's a 2. I'm going to store this 100 at index 2. And I'm going to increment my stack pointer. Now when I'm ready to pop, I use the stack pointer, but I don't just read the element at the index given by the stack pointer. I want the element before that. So to pop, I decrement the stack pointer, and then I read the number from that location in my array. So the general algorithm for push would be stack bracket SP is assigned the value of n, and then increment SP. Which I could also do in one line. So there's code for pushing. And it's a post-increment operation on the push. Okay, to pop, remember we wanted to subtract 1 from the stack pointer, and then use that as an index into our array. So subtract 1 from the stack pointer and then pull the element from that position in the array. That's how we pop, which we could also do by just saying pre-decrement. Does everybody remember what these built-in increment-decrement operators do? Right, so minus before a variable says subtract 1 from the variable and then use its value. If it comes after the variable, it says use its value, and when you're finished, then subtract 1 from the variable. And plus plus is the same for adding. So under this scheme, we do post increment for push, we do pre-decrement for pop. And our stack builds like this. And an empty stack, we can detect by the stack pointer being 0, and full, we detect when the stack pointer is equal to 10. Because if the stack pointer is 9, our next thing that we push is going to go into location 9. That's a valid location. And our stack pointer will get incremented to 10. That's when we know the stack's full. But that's just one way of doing this. We could use a stack pointer to tell us where we should pop from next. And so now when we want to push, we need to increment the stack pointer first, and then use that as a location to store our number. And when we pop, we would return the value at the current index location, and then we would decrement the stack pointer. So does this still do the same thing? Push of 15. Well, take the stack pointer, so stack pointer is equal to -1 to begin with. So this says increment the stack pointer to a 0 and store 15 at index 0. And now when we say push 20, it says increment the stack pointer to a 1, store 20 at index 1. And when we say push 100, increment the stack pointer to 2, store 100 at that index. And now when we say pop, we read the value at the index given by the stack pointer. Stack pointer is 2, so we're going to return the value at index 2, which is 100. But we're also going to decrement the stack pointer after we're done. And so here, SP will be -1 when our stack is empty. That's our initial condition. And what's SP going to be when the stack is full? It's going to be a 9. Because it means we've written something into here. SP is always the location of the first thing we should pop. If this is the last thing we've written, SP is going to be 9, and that's where it's full. And you can see if we try to push, first thing it's going to do is increment stack pointer to 10, and then try to store at that index, and that's out of bounds of the array. So here we have a pre-increment for push and a post-decrement for pop. So pre-increment, before we had a post-increment for push, And for pop, we have a post-decrement before we had a pre-decrement. Identical behavior, identical usage of the elements in the array, totally different implementations. Now, you're writing a main program that's using a stack, and you know that the stack is implemented like this, and you want to know if the stack is empty. And so your code very cleverly says, if SP equals -1, then stack's empty. You go to a different system, and you compile with their stack package, and they're doing this, and you say, if SP equals -1, stack's empty, and that's not true anymore. Because here, stack pointer equals 0 means that it's empty. So we're back to this idea of drawing a line between the user view and the implementation. Right up here, we would just call an isEmpty function. And if we're doing pre-increment, then down here, isEmpty would say, is the stack pointer 0? If we're doing post-increment, isEmpty would do something different. So that's that idea of that hierarchy again. All right, so there's at least 2 different ways to implement stacks using an array. There's at least 2 more ways to do this, because in both of these implementations, our stack started with element 0 and grew in this direction. That's not sacred. Our array stack has these 10 locations. We could start off with initializing the stack pointer to 9. And this is an empty stack. And this is next push location. And pushing a value n, we could say stack bracket SP minus minus equals n. And so when we push a 15, it's going to end up at location 9 and change the stack pointer to 8. And when we push a 20, it's going to store that at index 8 and decrement the stack pointer to 7, and so on. So here we have a post-decrement for push, and we can also do a pre-decrement for push. So you've got at least 4 different ways of implementing stacks with an array, depending on which of these strategies you use. Which one do you use? I don't know. They're all kind of the same thing, right? They're duals in some sense. But there may be implementation reasons why you'd use one over the other. Now, on some processors like ARM processors, there are configuration bits you can set up to actually tell it which style of stack you want to use. So that when you make a call and things get pushed onto the stack, is it doing post-increment? Is it doing pre-increment? Is it doing post or pre-decrement? You can control that. And it gives you all this flexibility. So lots of options there. I'm just flaunting the fact that I can walk away and still talk, and it's still recording. Did I already do this in this class? So there's our microphone level. Here, we'll do another test in this part of the room, because I walked to that part before. It seems to pick me up wherever I go, which is pretty good. So I could make you nervous and lecture from the back of the room and like tell you not to turn around. And I could use laser pointers and wireless mice.
I was just saying, what's the water?
Yeah, that's going to be interesting. Mm-hmm.
How long until the escalates to you, like, is this form of a cave and smoke machines? And
I'm working on it, man. Yeah. I'm hoping someone will do their SLP on, like, Raspberry Pi-based pyrotechnics. All right. So what does this look like in code? And we've already written a lot of it. So let's just do post increment, the first version that we went through, right? So init really just has to set your stack pointer to 0. That's all you need to zero out a stack. Push n just saves on your stack at location SP. Pop just returns with a pre-decremented stack pointer. IsEmpty just returns whether or not the stack pointer is 0. IsFull returns whether or not the stack pointer equals whatever the last index is. So if we created our stack to have 10 elements in it, then it would be full if stack pointer was equal to 9. And that's it. There's a working stack. Now, in C, we need to actually have an array somewhere. So our init routine might have a global variable declared outside of init so that it's persistent. And it could be something like integer star stack. So declare stack to be a pointer to an integer. And in init, we could say something like stack equals malloc 1,000 times size of int. And set your stack pointer to 0. And if I declare this variable outside of a function, it's global from that point on down. I could throw the keyword static in front if I wanted, but I don't really need it. And now stack's going to have a persistent value. So my init routine allocates space for 1,000 integers, has stack point to that, sets a stack pointer, and now we're all set to use our stack. And we can push and pop and so on.
So are you using the heap on
Mm-hmm.
So is that just the stack in the heap then?
Yeah, we got our stack inside the heap.
And you can do that?
Sure. You're the programmer. You can do pretty much anything you want. And it's just memory to the machine code, right? It doesn't really think too deeply about where it is. So
would that grow up or down then?
depends on the system. Heaps are strange, and they're not actually heaps. It's called the heap storage, but I'm told it's not actually a data structure heap. But stacks are strange when you look at the memory mapping. On a lot of systems, I don't know if I'd say most, but on a lot of systems, here's how your memory is set up. So around location 0, those locations are inaccessible. That's why you segfault when you try to use null and dereference it. Somewhere in here, you might have user code, and then there might be a big block of memory that's inaccessible, and then you might have system code, and a big block of memory that's inaccessible, and then you might have stack space down here at the bottom of your memory. And in this configuration, your stack would tend to grow upwards. The reason being that the stack might extend for as much memory as you have after you're done with the system code in this empty space. So if that leaves you with 50 megabytes of memory, your stack would start here and grow up 50 megabytes. If you've got 10 gigabytes of memory, your stack would start here and grow up 10 gigabytes. That would be a really big stack. But your memory usage is sort of scattered throughout different memory locations. And if you start your stack at the very end or close to the very end of your memory and grow up, right, you're not really bounding it. Whereas if you started at some location, you could only grow down to the last address in memory, which on a 32-bit machine would be 8Fs. But a lot of systems, they actually only use the first half down to 7 followed by a bunch of Fs, which is why that address always pops up when you're in GDB. You want to find the stack? Let's find our stack. Yeah, exactly.
Have you thought about getting like a little tiny whiteboard for up there, and then you can just erase that little thing? Instead of the numbers?
I almost went there, and I was like, no, I'm not gonna give in. I used to do that for making videos. I had a nice little whiteboard and could write on that. But you know, this Sharpie pen is gonna last me all quarter probably, and the whiteboard markers just don't. So I've also got a boogie board that I really love, and it's like a no battery, but it's a stylus, and you write, and it just electrostatically like pulls up. It does have a battery. Just pulls up. It's like an Etch-a-Sketch basically, but with a stylus. And that works really well, but it's a little small for this. That would be great, man. Yeah, we'd cover a lot of material.
I would tip you
Yeah.
if you could write code up there.
Check YouTube. I'm sure someone has done this.
Writing code.
Yeah.
How do you return carriage? I don't know. Yeah.
Let's control C, control F. Wait. What is it? Let's control L to clear the screen. Yeah, control.
All right, there's some useless code. Hope I forgot the good part. All right, there's some useless recursive code that's going to call itself. But if it's storing A as a local variable on the stack each time that it calls itself, we should get a new copy of A at a different location on the stack. So this should give us some idea of what our stack looks like. Yeah. Whoa. Oh, that's because I nexted. I blew up my stack. I needed to step. So let's look at the address of A. So that's where A is right now. If I step into the next instance of fun, and I look at A, it's now stored at EAAC instead of EACC. So it went down by 20 hex bytes. And if I step again, and I print the address of A, it should be 8C. All right, so our stack is somewhere around 7 bunch of Fs, EA, 8C, which means it probably started at 7 and a bunch of Fs, right? Which is just a gazillion ones. And it's growing with decreasing addresses, and each time that I call fun, my stack pointer is moving by 32 decimal bytes. Some of that is for a return address, and some of that is for the value A. So you can actually examine this memory location and see what's stored there. There's my 2. And so somewhere between here and here is the return address of the function, which I'm guessing might be this. I don't know if I can get to my program counter. Yep. So it's saving return addresses, it's saving local variables, it's also saving other information. So this is what we call a call frame. But yeah, so it's starting around that 7F and growing to lower addresses. This was how we learned about stacks and stuff in my day, because we didn't have books. All right, let's see. I mentioned this in the other class because it came up, just so you get the same thing. There's at least 2 kinds of memory that we're talking about. There's physical memory, which is that memory stick you put in your laptop, right? 16 gigabytes goes from 0 to 16 gig minus 1. And it's just sequential locations, byte by byte by byte. But our memory that the CPU interacts with is what's called a virtual memory. And in general, it's much bigger than the physical memory, right? We don't have enough physical memory to store some of those addresses that we were looking at, right? The 7 with all those F's after it. So it can look like it's bigger than the actual physical memory, and not all of it exists, right? Some regions like this don't exist. If you try to access something from there, you get a segmentation fault, right? Segmentation meaning looking at which segment of the memory we're trying to access. There was an error. And some of this stuff may be scrambled up. All right, so there's a mapping from virtual memory to physical memory. Now we're into a computer architecture, different course. But memory management is a big piece of computer architecture, and it's sort of how we translate the addresses that our CPU deals with to the actual physical memory. And it's nice because my memory can look like this, and your memory can look exactly like this. It starts from 0 and it goes up to here in the stacks of these addresses. But your memory might be mapped to a different section of physical memory. So you think you're accessing location, 600010, and I think I'm accessing that location also, but they're actually different locations in physical memory because that address is mapped to different spots. So memory management is a separate topic, but it's fun stuff. All right, well, stack implementation. So I threw a malloc statement in our init code that allocated 1,000 integer spaces, space for 1,000 ints. And if I try to push 1,001 things, I'll get a stack overflow. This is a downside to using arrays to implement stacks, is that you usually have a fixed size for the array. Now you can do things like, if you try to push and you're out of space in the array, you can create a bigger array, copy everything over, get rid of the old array, and now my array goes up to 2,000 elements. And if I fill that up and I still want to push more, I might make a 4,000 element array, copy everything over, right? So you can have your stack dynamically grow or shrink over time. That's fairly intensive when you get to the point where you've got to copy everything from the old stack to the new. But there's different ways to, different approaches to implementing a stack. So one way would be to use a linked list. And I haven't decided, but I think this is what you're going to do for PA3. You're going to use lists to implement queues and stacks instead of using arrays. So how do we make a list-based stack? Remember, first in, last out. Last in, first out. So all we got to do is preserve that kind of access order. So let's make a linked list. And I'll call the sentinel stack. And an empty list is going to correspond to an empty stack. So an empty stack, if I check the sentinel node, it's not pointing anywhere. It's pointing to null. I know my stack's empty. Now when I want to push, insert right after the sentinel. So I say push 20, make a new node, set the data to 20, see what the sentinel is pointing to and have my new node point there, and then change the sentinel to point to my new node. There's my stack containing a single thing, 20. If I want to push 35, same drill, make a new node, set the data to 35. Take what the sentinel is pointing to and have my new node point to that. And then have the sentinel point to my new node. So what does this look like in code? So let's say push n. So make a temporary node, right, by using malloc. Set the data to be equal to n. That puts my number up there. And then we want the sentinel to point to this new node. We want this new node to point where the sentinel was pointing. So before I change the sentinel, let's use its value. So let's say temp arrow next equals stack arrow next. And then stack arrow next equals temp. There's my push routine. So now if I push 100, I make a new node. This is temp. I said temp data equal to 100. I said temp next equal to stack next. Well, stack next is pointing to the 35, so I set temp next to point to 35. And then I set stack next to be equal to temp, so stack next points to my temp node. And it's easier than what you've done in PA1 and what you're doing in PA2, because you're always inserting right after the sentinel. So my sentinel points to 100, that points to 35, that points to 20, 100, 35, 20. I've got my nodes in reverse order from what they were inserted in. So pushing is straightforward. And popping is even more straightforward. So I'll draw my nodes so they look a little more locationally meaningful. All right, so that's the same linked list as what we had. Stack points to 100, points to 35, points to 20, 20 points to null. So 135, 20, null. So how do we pop? Well, we want to pop the first node after the sentinel. So take the thing that the sentinel points to, that's stack arrow next, and look at its data field. And we're going to save that in a temporary integer. And then we want to have the stack point to the thing that have the sentinel point to the thing that that first node was pointing to. So I'm going to make myself a temporary pointer to what the stack is pointing to. So this is temp node. And then I'm going to say stack next equals temp node next. So now stack's going to point to whatever temp node was pointing to, and that node has been popped off. Why did I use a temporary variable here? What's the one more thing I want to do? Free. And if I free right, so if I don't have a temporary variable, once I change stack arrow next, I've lost the address of this node. But if I free this node, I can't look at its next value anymore. So temp node next is going to be meaningless once I free temp node. So I need a placeholder in between there. So free the temp node, that releases that from memory, and there's our new stack. So what can go wrong here? Well, if I try to pop from an empty stack, I'm going to have a problem. So if my stack looks like this, as soon as I say stack arrow next arrow data, I'm going to segfault. So I need to make sure my stack's not empty. So just check to see if stack arrow next is null. And if it is, can't pop it. And this also lets me write an isEmpty function. I need to pass stack to my pop routine if I'm doing this. I've got to keep track of it. So isStackEmpty just see if stack's next pointer is null. And if it is, your stack's empty. If not, it's not.
Wouldn't your if one be if it's not null?
IsEmpty will be true if that conditional statement is true also, I believe. So if stack next is null, then it's empty.
I was talking about the top if statement.
Oh, at the top? Yeah, if stack next is null, then it's empty. So
Oh, then the rest of it is like an else.
yeah, so you'll do a return or set an error code or blow up or something, yeah. So how do you know if your stack is full? Yeah. So right here, see if temp came back null. And if it did, you're out of memory, so technically your stack is full. There's no space left to add anything else to it. So there you do a condition. How do you write an IsFull routine? Well, that's harder to do. You could try malloc-ing something and see if it succeeds, and if it does, then you could free it and say, yeah, there's probably space. But that's a little goofy, right? Because somebody might allocate memory in between, and then you're out of space. So we probably wouldn't have an IsFull function, but what we could do is have our push return a value that tells us whether it succeeded or not. So now when you push something, you check the return value. If it's 1, you succeeded. If it's 0, then you failed, meaning you're out of memory. But on a stack like this, it's pretty, the only time you're really going to run out of memory is if you're stuck in a loop. If you're looping and you're pushing things without ever popping, and eventually it'll blow up. That would have been a fun exercise. So how many times will this call itself before it blows up? Oh, I do need standard I on it. All right, we'll let that run. All right, so you don't generally fill up your stack if you're using an array. So in C, we gotta deal with some variables, right? So our main program is gonna have to know something about the stack. This clean division between user code and implementation C doesn't really lend itself to that perfectly. When we start talking Java and Spring, we'll see how Java supports that kind of clean division for an abstract data type. But in a main program, we might do something like this. So we need to know some sort of structure stack. And it might have well, it's just a linked list. So you toss that in an include file and say, when you want to use a stack, include stack.h, and they'll do that for you. And you tell the person when you want to define a stack, you say struct stack star my stack. And you could define a macro for them that would let you do that. So you could define something like a init stack that you just put the name of a variable in, or whatever. So to initialize a stack, you use my stack equals init. And when you want to push something, result equals push. But we got to tell it what the stack is we're using. So we could pass that as an argument. And for pop, we could just pass it the stack we're using. And if we had an is empty, we could call it like that. Yeah?
Is init like a formal function for starting something?
No, I mean, it's what I use in these examples, but it's just a function.
I noticed the Android development thing also uses init
Yeah.
as like a start thing, so I don't know if that's, I didn't know if that was like.
I mean, if you want a short function name, it's probably one of the first ones you'll come to. But I would probably call this initialize stack or something, as opposed to initialize linked list or initialize something else. But yeah, it's just kind of common terminology, I guess. And then on Unix, of course, there's the init process, which is the first process created that farms off all the other processes, including really bad ones that are going to run away and blow up the stack. Oh, that didn't take long. 262,000 calls. That's tiny. I'm surprised. All right, so in C, we have to do things like pass the stack itself to our functions, which requires us to know that it's a structure, and so on and so forth. But it works. And same thing if stack was built using an array, right? Our structure would change. But we could call these things exactly like we were before, and we shouldn't have to change how our main program's using this stack. All right, the imperfect part is we need to know something about the structure to be able to declare it and such, but we can get rid of that in Spring. All right, other questions, comments? All right, so Wednesday we will talk about queues, and we'll look at queues as an abstract data type, and we'll look at uses for queues, and then we'll talk about implementing queues. Implementing queues with an array is trickier than implementing a stack. We need what's called a circular buffer. Implementing queues with a linked list is slightly more complex than implementing stacks with a list. But with a small modification using a circular list, it'll be pretty easy to do a list-based. All right, I will see you next time.